The invisible engine behind extreme weather. It was the middle of the night. There was nothing unusual at first. No storm sirens, no dramatic warnings, just cold. Far colder than this place had ever been designed to endure. Then the lights went out. Heating systems shut down one by one. Pipes froze. Emergency lines flooded with calls. People did not die because of the cold alone. They died because the systems meant to protect them stopped working. And this wasn't an accident. It wasn't random. It wasn't simply bad weather. What failed that night was something invisible. A system operating far above human attention. When disasters happen, we reach for simple explanations. We say the climate has always been unpredictable, that nature is chaotic, that extreme events are just bad luck. But the atmosphere is not random. It is structured, layered, governed by physical laws. Every movement of air follows gradients of temperature, pressure, and energy. When these gradients are stable, weather behaves in familiar ways. When they weaken or distort, the entire system begins to behave differently. Extreme weather is not the absence of order. It is often the result of order breaking down. High above the Earth's surface, over the polar regions, a massive circulation of cold air is constantly spinning. This is the polar vortex. Despite how it's often described, it is not a storm that suddenly appears. It is always there. Think of it as a containment system. When it is strong, it locks the coldest Arctic air in place, preventing it from spilling southward. Winds inside this system can reach incredible speeds, forming an invisible wall around the pole. As long as that wall holds, the planet's weather remains relatively stable. What most people don't realize is that the polar vortex exists on more than one level. There is one in the stratosphere, tens of kilometers above the surface, and another in the troposphere, where clouds form and storms develop. These two systems are connected. When the upper vortex weakens, its influence slowly travels downward. What begins high above the Earth can take weeks to reach the surface. By the time we feel it, the process has already been unfolding for a long time. If Earth were perfectly smooth, this system would rarely fail. No mountains, no continents, no oceans separating heat and cold. But Earth is uneven. Mountain ranges, land-sea contrasts, and temperature differences bend the flow of air around the planet. These bends form massive atmospheric waves, called planetary waves. Most of the time, these waves move horizontally, guiding weather systems from west to east. But sometimes, they grow stronger. They rise upward, into the stratosphere. When these waves collide with the polar vortex above, they act like a shock. The vortex slows down. It stretches. Sometimes it splits. This can trigger a phenomenon known as sudden stratospheric warming. Within days, temperatures high above the Earth can increase by 30 to 50 degrees Celsius. Winds weaken. Some even reverse direction. The wall that once held the cold in place begins to collapse. When the polar vortex weakens, the cold air it once contained doesn't disappear. It moves, slowly at first, then suddenly, southward, into regions that were never designed to handle it. This movement is not instant. There is often a delay, 1 to 3 weeks, between disruption in the stratosphere and extreme weather at the surface. By the time cities freeze, the process has already been unfolding far above. This is why extreme cold can arrive without dramatic warnings. It feels sudden, but it isn't. Here is the paradox. A warming planet does not eliminate cold extremes. It destabilizes the system that once kept them contained. When the jet stream becomes weaker and more distorted, it begins to stall. Weather patterns stop moving. Cold air lingers longer. Heat gets trapped. This is how heat domes form. High-pressure systems lock hot air in place, sometimes for weeks. The same broken circulation that allows Arctic air to spill south can also prevent heat from escaping. Different disasters. Same underlying mechanism. Scientists agree on one thing. The Arctic is warming faster than the rest of the planet. What they still debate is how this warming affects the polar vortex. Some argue that reduced sea ice and weaker temperature gradients make the system more unstable. Others caution that atmospheric systems have always been variable, and that current data records are too short to confirm a long-term trend. Satellite observations only go back a few decades. That's a short window for a system that may operate on cycles lasting centuries. But uncertainty does not mean safety. Modern society is built around averages, average temperatures, average demand, average conditions, energy grids, transportation networks, food systems, all optimized for what is considered normal. Extreme events expose the limits of this design. Power fails, supply chains break, infrastructure collapses. Not because the systems are poorly built, but because they were never designed for this level of instability. The polar vortex has been known to science for more than a century. Yet most people only hear about it after disaster strikes. Not because the warnings weren't there, but because invisible systems are easy to ignore. The atmosphere above us never stops moving. Every shift carries consequences. The real question is not whether extreme weather will happen again. It's whether we are learning to recognize the signals or waiting for collapse to force our attention.